Hello, today we're going to look at 4.2 extreme values. So number C is a critical point if it is in the domain of f and either f prime of C is equal to 0 or it is undefined. So both of those things have to be true. Find all critical points of f of x equals x cubed minus 9x squared plus 24x minus 10. Most of the time this is going to occur when it's equal to 0. But the undefined is something to keep in the back of your head. Those would be any moments where we know that it's, maybe 0 in the denominator or something along those lines. So ultimately you have to derive first. So 3x squared minus 18x plus 24. And then we can say to ourselves, well, would this derivative ever be undefined? And the answer is no, because it's still a polynomial and there's no domain restrictions here. So we would set it equal to 0 and solve. So I can divide by 3. Right, I can factor. I can solve. So x is equal to 4 and x is equal to 2. So those would be the x values when the domain is 0. I'm sorry, not the domain, the derivative is 0. And it's saying to find all of the critical points. So we're going to take those values and plug them in to the original equation to come up with the ordered pairs. So f of 4 that would give us negative 6. So 4 comma negative 6 is a critical point. And f of 2 is equal to 10. So 2 comma 10 is the other critical point. Okay. F of x equals the absolute value of x. So when we take a look at the absolute value, this is something that we're going to analyze a lot more this chapter. Right? Remember that there was that moment that we talked about a function might be continuous but not differentiable, and that happened at corners, cusps, etc. Well, remember that the absolute value's vertex creates a corner. So that's a moment that we are definitely undefined, right? So we don't really have to derive this. We would have to think of it as a piecewise function, right? The right side has the function positive x, the left side has the function negative x, and they meet there at the origin. So graphically speaking, I am thinking about the derivative. If this were a harder function, then I would walk through the derivative algebraically. But anyways, we're just acknowledging that the derivative at 0 is undefined, and therefore 0 comma 0 is a critical point. Okay, I'm going to leave this example for you all to do. It's the same idea. We just have a chain rule embedded in here. I'm going to move on to this one with trig. So find all critical points from 0 to 2 pi. Oftentimes, trig is restricted on the domain because, of course, we know that it wouldn't just continue. So we're going to derive this. Before I do that, I want to remind you all again that when you have an exponent on trig, you want to rewrite that. So it's clear that it's sine theta quantity squared. That way you're acknowledging that the outer function is the squared, the inner function is the sine theta. So cosine theta derives to negative sine theta. Sine theta quantity squared goes to 2 sine theta cosine theta. Set equal to 0, because this would not be undefined anywhere. Factor out of sine theta. And you're left with that. So again, set equal to 0, each factor and solve them. So win is sine 0? And when is cosine a half? So thinking about your unit circle, sine is your y-coordinate, right? So it is 0 when theta is equal to 0, pi, 2 pi. When is cosine a half? That's going to occur at pi over 3 and 5 pi over 3. And I have to take these values and plug them back into the original. Right. Let me give you a little mini lesson on your unit circle in case anybody's like, oh my gosh, I can't remember any of those things. So with the pi over 3 one, I think that being logical through the sine theta equaling 0 is fine. But thinking about, well, why is it 1/2 at pi over 3? So remember that you have your 30, your 45, your 60. You have to remember, of course, that cosine is the x, sine is the y. Right? You have to remember key numbers like 1/2, √3 over 2, √2 over 2. Then you can think of them as triangles, right? The first angle is 30 degrees, and right, we have our unit circle. That's a little squiggly. And if I take that first triangle, that first angle, and turn it into a triangle, it looks like this. So if I were to say to myself, what is larger on that triangle that I just sketched, the base or the height, I would say the base. Right, my base is certainly longer than my height is. So out of these two, not those two. Out of these two numbers, √3 over 2 is larger. So therefore my x-coordinate right here has to be the √3 over 2. Okay. And then if I did the same thing with the 60, I'm going to skip over the 45 because those are the same. But if I did the same thing with the 60, now I would say to myself, well, the height is larger than the base. So now it has to be 1/2 comma √3 over 2. So at 60 degrees or at pi over 3, my cosine, my x, is 1/2. So you can think about the length of the bases and the heights in the first quadrant to help you get those ordered pairs straight, and then you work around your unit circle, of course, with the correct signs. Okay, just to finish up this problem, remember we have to evaluate this function at each of these critical moments, critical thetas, so that we can come up with ordered pairs. So if I evaluated at 0, we would be looking at cosine 0 plus sine squared 0, and we would have a 1. If we did it at pi, we would have a -1. And if I did it at 2 pi, I would also have a +1. Then if I take a look at pi over 3, right, cosine at pi over 3 is 1/2. Sine at pi over 3 is √3 over 2 squared. So that's 9/4 plus 1/2. I'm sorry, not 9/4, 3/4 plus 1/2. So I'm going to get 5/4. And if I evaluate it at 5 pi over 3, I'm also going to get 5/4. Okay, so those are all the critical points on the graph. So here we're talking a little bit more vocab. So extreme values are the min-max values of a function. Absolute extreme values are the min-max values of the entire function or on a given interval. And local extreme are the min-max of a part of a function. So we're really looking at those two words, absolute versus local. Extreme is kind of that overarching definition. We talk about absolute extrema, right? Is it the largest value everywhere, or is it a local? Just a turning point. We usually use turning points the most. But sometimes our absolute is helpful as well. Okay? Okay, so again, absolute is the largest point on a set interval, mostly the entire function, and then local is just within that region, just where that turning point is. Okay, so how do we find these extreme values? First, we find the critical points, just like we were doing. Then we're going to test the end points, so the domain restrictions, and the critical points into the original function. The lowest y value is your minimum. The highest y value is your maximum. The overall height is what we're looking at. So we start by finding the min and the max on the given interval from 0 to 6. So we derive we set equal to 0. It's not undefined because it's a polynomial. I can divide by 6. So x is equal to 4 and 1, right? So I need to test, those are my critical points, and I need to test my endpoints. So I need function values for 0, 1, 4, and 6. You can use your graphing calculator, go to the table of values, and extract those function values from it, right? Just type that into the y equals and go to your table of values or go to Desmos. So the answers that I'm getting from my calculator are 7, 18, -9, and 43. So the overall smallest number, -9, that gives me my absolute min from 0 to 6. And 43 gives me my max. We do not know if these are turning points or not right now. All I know is that they are absolute mins and maxes. That's what we're analyzing. So I'm going to leave this example to do together. As well as that example. And let's move on to one more with the ln. So find the min and max of this function. So we have x squared minus 8 ln x. So f prime equals 2x minus 8 over x. Set that equal to 0. 2x equals 8 over x. If I multiply by x, so I can kind of move things around here, I would have 2x squared equals 8. So I have 2x squared minus 8 is 0, or x squared minus 4 is 0. So x is plus and minus 2. So I need to throw away the -2 because it's not in my interval. So I'm only doing 1, 2, and 4. If I went to my graphing calculator to get these values, I would have 1, -1.545, and 4.91. So I have my minimum and my maximum. Okay. Another theorem in this section that I want to go over, it's called Rolle's theorem. So assume f of x is continuous on AB and differentiable on AB. And if f of A equals f of B, then there exists a number c between A and B such that the derivative is 0. So Rolle's theorem is guaranteeing a local min or a local max. Right? If we have A, B, and C, and f of A equals f of B, even if, right, some of you might be like, well, what if the function does this? Even if it does that, right, the derivative everywhere is 0, so it still satisfies it. But more commonly, right, if I have something like this going on, at C, I have that turning point, and my derivative would be 0. So I'm just guaranteeing it's there. I'm not sure exactly where, but I know that it is there. So using Rolle's theorem, verify Rolle's theorem for this function. Okay. So the first thing I want to do is find the function values each of these, -2 and 2. So I'm going to get 16 minus 4, 12. And if I do the same thing with 2, because it's an even function, I'm also going to get 16 minus 4, or 12. So my f of a equals f of b. Okay, so now I'm going to go to my derivative and show that the derivative is 4x cubed minus 2x, setting that equal to 0. And solving, what I'm looking for is that 0 between -2 and 2. So x equals 0. There's one of them. And there's actually 2 more, right? Plus and minus the square root of a half. So that's just showing that, of course, that these zeros did exist. Only one of them had to exist, but there happened to be 3. And that's it for 4.2.